So this is, let's say, function g. But whatever is the function that I am defining, element, every element will be a member of this vector space, and every element is known only in those discrete points. So I can say that this f, I will define it as the value at x1, value at x2, etc., value at xn. Similarly, g also is known at x1, at x2, etc., at xn. Correct? So f is also known only at those points, g is also known only. So with this knowledge, you know that it's an n-dimensional vector space. Because every function is only known, it is like 5 darkies to real number. It's a 5-dimensional vector space. So here we know only n darkies, only n points. So n points, you have n complex numbers. So it's an n-tuple. So you have set up all these vector spaces, set up all these vectors will form an n-dimensional vector space. So it's a finite dimensional vector space. So I can define an inner product between f and g, as sum over j is equal to 1 to n f j star gg. No problem, because we have already defined it in this fashion, and let me consider all the weights to be 1 to start with. You can, all the arguments will go through if weight is put also, but let me consider this as my inner product. In particular, if I consider f, then I will have this sum over j is equal to 1 to infinity modulus of fi square. Okay? Now, if I repeat my argument by saying I have more and more information about this function, that means I am getting a new equipment which can give me values of this property at intermediate values of x, or I have a better algorithm which gives me solution at intermediate values of x, then what happens? I am going to get information at more and more points. So this vector space, this vector, so I am going to have more and more information at these points, like this. Then what happens is this length goes on, at this point it is n, but then if I ask this question, that what happens to this f comma f, in the limit I get information, I get this function at every value of x. So what happens? This becomes limit n tending to infinity sum over j is equal to 1 to n mod fi square. But this definition of inner product is erroneous, because every mod fi square is a positive quantity. So this will be sum of infinitely many positive quantity which is infinite. And you will get this answer for every f that you choose. So the norm of all vectors is infinity is meaningless, because that's not a useful definition for infinity, for the norm at all. You should be able to differentiate between vectors and their magnitude. So this cannot be a definition for magnitude, because this goes to infinity. Since modulus of fi square j square is greater than 0 for all I. So it's a sum of infinitely positive quantities is itself infinite. So I cannot have this as a definition. So this cannot be the definition of the norm. Since this norm is induced by this inner product, this cannot be the definition of the inner product. So now what can we do? Since this quantity is going to infinity, you must multiply with some quantity which goes to 0 in this limit, and then the product remains a finite quantity. Now, if I consider the spacing between these 2 points as delta, as n increases, that means more and more points are known, this delta becomes 0. Correct? So I can always reformulate define this f as limit n tending to infinity, limit delta tending to 0, sum over j is equal to 1 to n mod fi square into delta. Since this quantity goes to infinity and this quantity goes to 0, this product is finite. This product is finite. Now this can be written in the limit of these two things. This can be written as integral from 0 to 1 f of x. That means at every value of x, I know f, delta will be dx. So this is like a Riemann sum of this integral, or this is a Lebesgue integral of this sum. So in that sense, you can formulate this as an integral. So for continuous functions, the inner product has to be defined. So generalizing this, for functional spaces, the inner product, the most general inner product between two functions f and g is given by integral, whatever is the domain on which these f and g are defined, some w of x, some weight function, and f star of x, g of x, where w of x is greater than or equal to 0 for us. This is called a weight function. Just like discrete weights we had, we can have a weight function. Some functions are orthogonal only if you define an appropriate weight function. For example, you may recall Hermite polynomials. They are orthogonal polynomials only if you have e to the minus x square as a weight function. Lagrange polynomials, they are orthogonal polynomials only if you define weight function as e power minus x. Okay, so there is Chebyshev polynomials. They are orthogonal functions if you define w of x as 1 by square root of 1 minus x square, and so on. So weight function is important because you can define orthogonality appropriately. So this is the most general definition of an inner product of vector space of functions. Okay, and in quantum mechanics, this is what we use. In some problems, Wx comes automatically from the Schrodinger equation, like in harmonic oscillator. You get Hermite polynomials as solutions, and e to the minus x square directly comes from the Schrodinger equation as a ground state wave function. So, wherever physically some orthogonal polynomials are relevant, the wave function gets picked up. Okay, so this is as far as inner product is concerned. So we have defined inner product in general for vector spaces of finite dimension. If you have infinite dimensional vector spaces or function spaces, then you can define inner product in this fashion. So now I will define. So one result I would like to prove is if we have a set of orthogonal vectors, okay, so let V1, V2, V3, etc. Vn are a set of orthogonal. What does it mean? It means they are mutually orthogonal. Inner product of V1 with V2 is 0. This implies any Vi, comma Vj is equal to delta I. Okay. Normally, if Vi is same as Vj, it is not necessarily 1. It should be greater than 0. That's all. If it is also equal to 1, that means each vector has a norm equal to 1. So that means each vector is normalized. So if we have a set of vectors that are mutually orthogonal and each vector is normalized, we call such a set as orthonormal vectors. Okay? So I may simply write this as set of orthonormal vectors. That means if I equal to j, it is equal to 1. If they are not normalized, then it need not be 1. That's the only difference. Now, the claim I would like to make is they are linearly independent. They are linearly independent. How do we prove this? It is intuitively easy to understand. Geometrically, orthogonal means wherever we can visualize, you have one vector, there is another vector, so they are perpendicular to each other. So if they are perpendicular, then they cannot be dependent on each other. So if they are orthogonal, they have to be linearly independent. So the proof is rather intuitively clear. But how do we prove that? If we have to show these vectors are linearly independent, you have to consider alpha 1 V1 plus alpha 2 V2 etc. alpha n Vn is equal to 0, where alpha 1 alpha 2 are scalars. Correct? So, and now I have to show that alpha 1 is 0, alpha 2 is 0, alpha n is 0. How do I show that? Suppose I take, so this will be 0 vector, that's what it means, right? This is a null vector. I take inner product of left hand side with V1, that is V1 comma alpha 1 V1 plus alpha 2 V2 plus alpha n V2. What will this be equal to? 0, because right hand side is 0, inner product of any vector with 0 is also 0. But what is this? Because this linearity property is there for the inner product. This is nothing but alpha 1 V1 comma V1 plus alpha 2 V1 comma V2 etc. alpha n V1 comma Vn is equal to 0. But we have already started with the condition that V1 they are mutually orthogonal. That means what is V1 V2? 0. V1 Vn 0. Only V1 V1 is not 0. This means what? Alpha 1 is equal to 0. So I have shown alpha 1 is equal to 0. Now I take inner product with V2, I will get alpha 2 equal to 0. With V3, I will get alpha 3 equal to 0. So in general, I may take with this Vj, then I will get, Vj, then I will get alpha is j equal to 0, and this is true for all 1 less than or equal to j less than or equal to j, and hence they are linearly. So the same proof I will generally extend it to every other coefficient. So alpha j equal to 0 for all j means they are linearly. But important thing to note here is that the converse is not true. What does it mean? That means vectors that are linearly independent are not orthogonal. You may have some vectors that are linearly independent, but they are not orthogonal. That is, a set of linearly independent vectors are not necessarily orthogonal. Orthogonal vectors are always linearly independent, but linearly independent vectors are not necessarily orthogonal. It is easy to construct an example. Let's take a simple